All right. Welcome, everyone. I think the last week we kick off our seminar series with Vancy Mao lecture, in person, virtual, and on YouTube was a great success. There is a big control boss underneath this. So therefore, the boss of the seminar series tells me I have to read from the script. So excuse me, my reading from script. So welcome everyone to our BME seminar series hosted by the Department of Biomedical Engineering. My name is Ed Guo. I'm the chair of the Department of Biomedical Engineering here at Columbia. Today, we continue offer this lecture in hybrid format with both virtual and live audience in here. So our speaker will present approximately 40 minutes. We will leave about 15 to 20 minutes at the end for question and answers. For our virtual audience, throughout the presentation, please using the Q&A features at the bottom of the screen, not the chat. To submit your question, we will try to answer as many questions as possible during the Q&A sessions. And for our live audience, you will also have a chance to ask a question in person during the question period. We're just asking our speaker to repeat the question from our live audience, such that for the benefit of the virtual audience. Okay, so today we're excited to welcome Juergen Hahn. And Dr. Hahn is the head of Department of Biomedical Engineering at RPI, Rensselaer Polytechnic Institute up north. And then our founding chair, Vancy Mao, received his bachelor's and PhD from RPI. And also in the department, in the applied mechanics department, has a Vancy Mao lecture as well. So it's very glad to have Dr. Hahn coming here. And Dr. Hahn also holds a joint appointment in the Department of Chemical and Biological Engineering. His research interests include system biology, process modeling, and analysis, and over 140 peer-reviewed publications in print. Dr. Hahn has received several awards and was elected to the MB Fellow in 2013 and the AICHE Fellow 2020. He served on the IEEE CSS Board of Governors in 2016 and has been CATCH trustee since 2014. He's currently serving as Deputy Editor-in-Chief for the Journal of Process Control, as well as editor for Journal of Optimal Control Applications Methods, as Associate Editor for Journal of Control Engineering Practice and Journal of Advanced Manufacturing and Processing. Welcome, Professor Hahn.
Can you?
Yes.
Okay. So can everybody hear me? All right, well, thank you very much for the introduction. And it's a pleasure to be here. And you stole some of my thunder. I mean, coming from RPI to Columbia is a special thing because we actually have quite a nice connection between the departments. And so it's my real pleasure to visit here. And in fact, this is my first in-person seminar in about 1.5 years. So a few more to come. Other places, but couldn't be at a better place. Thank you for having me. So the topic of my talk will be towards the development of a diagnostic test for autism spectrum disorder. Data science meets metabolomics. Just as a disclaimer, my background, I'm come very much from the data science aspects from this, and that's where I'm going to focus on as well. But before I get into the details of the talk, I want to say a few words about my home department at RPI. Yeah, some of you may be familiar with it, others may not. There may also be some undergraduates in the audience, and who knows, maybe you think about graduate school. It doesn't hurt if I actually say who we are, what we're doing. So Rensselaer is actually the oldest technical university in the US. We're almost 200 years old, And we're located in the US, in the capital district of New York, roughly 2.5 hours north of here. If you basically drive along the Hudson, you get straight there in the Albany, Troy area. We're a polytechnic, so we're a much smaller school, 7,000 students, but 80% in science and engineering. Very STEM heavy with what we're doing. Our department is actually reasonably old. We awarded the first bachelor's degree in '67. The department was then founded in '74. Given that, I mean, we're the youngest department actually at RPI in biomedical, but we're one of the oldest ones in the country as a whole. We have over 50 of our former students of faculty members, and some of them have even connections here to Columbia as well. So even though BME is the youngest department, we're also one of the most popular and one of the most research active ones. So we have a total of 13 tenure track, tenured faculty. 2 of them are administrators, so it's actually 11. We have almost as many R01s as we have faculty. We have 2 NIH T32 training grants. If you look at outputs, I mean, we're producing over 8 papers a year per research group, and research expenditures are north of 400K. So we're in a very good position. We're a small department, but we like to do high quality work. Now, the research areas, I mean, they don't span everything that you do in BME because we're simply too small department, but we have people in biomanufacturing. We have a very strong imaging group and image analysis. We have some people looking at biomolecular science, which gives more into the pharmaceutical space. Obviously, biomechanics with all the history that we have had there. My work is more in the systems biology, and then obviously we have a reasonably sized tissue engineering group as well. Okay, that's kind of about RPI. If anybody has questions about that, I'm more than happy to talk to you afterwards or per email or whatever. So let me go back to my talk then. This is about autism spectrum disorder, which is probably something that you haven't heard a lot of research talks about because the community work in this is not particularly large, which is interesting because it is something with a relatively high prevalence and also a very significant impact. The reason for this is really more historical. Historically, autism was very much driven by psychiatrists. So other medical professionals as well as engineers have only really gotten involved more in recent years. And when you already look at the definition, so does somebody have autism or not for diagnosis, it just said, do you have difficulties with social communication interaction, or do you have, or is there expression of restricted repetitive behaviors and interest? If the answers to these things is yes, then basically somebody gets a diagnosis of autism spectrum disorder. Clearly, these are things that if you give somebody a questionnaire or you observe them for a while, you get an answer, but they don't tell you at all what's going on in the body. Now basically, if that's all you're interested in is if somebody has a diagnosis, that's fine. But what you find is that there's so much more going on in the people who are diagnosed with this. They have many co-occurring conditions. This starts with there is a good percentage of people with intellectual disability at the same time, ADHD, almost all have speech and language delays. The chance of having epilepsy, if you have autism, is 10 times as high as normally. There are sleep disorders. You could argue like, well, at least all of them focus on the brain, and so getting psychiatrists involved is not a bad idea. But many people also have GI problems. Now, that is certainly you cannot directly explain with the brain. There's the gut-brain axis. I agree with that, but clearly this affects the body as a whole. Lastly, if you look at the number of people getting diagnosed, and I'm basically just plotting here the data. And by the way, this is the official data from the CDC. I mean, it says Autism Speaks there because they generated the graph. I did not. But the data comes from the CDC, and you see that there's been a 3-fold increase since 2004. There are some people who go back to the 1970s when the prevalence was 1 in over a few thousand, and now it's 1 in 54, which is 1.9% of the population. Well, population under the age of 8, that's where this is diagnosed. So going back to the 70s, in my opinion, isn't a particularly good idea because our data wasn't that good. But over the last 15 years, how we diagnose has been reasonably stable. And so this is both a significant increase as well as we have a significant number. One last thing that I want to mention here is motivation. and this is really unfortunate, but there is somewhat of a disconnect between how autism is portrayed in the general media and then when you look at the scientific literature. Yeah, in the general media, you often get this idea they're saying that, well, those are people, they may be a little quirky, but other than that, everything is perfectly fine. Yeah, and autism is very heterogeneous disorder. Yeah, so there are people around like this, but the majority are not. Yeah, and to give you some ideas, I mean, just look at average lifespan. For most people who are healthy, it's around 80. Anybody want to guess what it is for somebody with an autism diagnosis? Yeah, 1/2, 40 years. Okay, that's clearly significant. All right. The other thing is also then when you look at, so what are the common causes of death for people? I mean, usually it's cardiovascular disease, stroke, yeah, cancer, those are up there. If you look at what it is for people with autism, it's drowning. Yeah, so clearly because the majority needs pretty much 24/7 supervision, and if they don't, then actually bad things can happen. So I said, I'm not saying that everybody's affected by this, but it's basically, it's a very heterogeneous group. Yeah, and so that's one of the things that got us interested. Anyway, to recap some of this, the latest CDC number says 1 in 54 has autism. For some reason that we really don't understand yet, boys are 4 times more likely to be diagnosed than girls, and 95% plus have other co-occurring conditions that you cannot directly link to ASD. Yeah, if you look at the cost for individuals over lifetime, and this is 2015 numbers, so probably a little higher now, yeah, was around $1.5 million for an individual. If they also have intellectual disability, and that's roughly a third of the children who have this, then we're looking at $2.5 million per individual. For society as a whole, I mean, we're looking at over $250 billion. Yeah, it's in the same ballpark as what we spend for depression, ADHD, Alzheimer, or diabetes. Yeah, one of the reasons you don't hear as much about it is the cost is different. Yeah, if it's for diabetes, the cost is mainly medical, which you can directly associate with something. Here, a lot of this is basically special education services that school districts have to do, and so they're more the costs are more local rather than central. And that makes it harder to figure out what it is. But it is, I mean, it's actually slightly above the numbers for these other conditions here. Yeah. So one thing that people generally can agree on is that the earlier you can diagnose autism, the better the outcomes. Okay. And the outcomes in this case, we're looking mainly at behavioral therapies. Yeah, like applied behavioral therapy and a few others. So people agree with that. And ideally, you would like to diagnose children at 18 to 24 months. If you could do it earlier, perfect, but people aren't sure that's possible. But 18 to 24 seems reasonable. But in reality, right now, the average age is slightly over 4 years. Okay, and part of that is if you're trying to figure out if a 2-year-old is developing normally, well, there's a gazillion different ways how they can develop normally. Some people start talking a little later. That's usually one of the indicators. Yeah, but the other thing is also that I mean, it's certainly not easy to diagnose a 2-year-old with something. Yeah, and so if you go to a specialty clinic where all they do all day long is diagnose people with autism, they probably can catch this much earlier. But if you're living in a rural area or in a city area or something where any place where the healthcare system is stressed, this is going to take longer. Usually, the diagnosis happens when everybody's already absolutely sure what's going on, and so the average age is over 4 years here. You can go to other countries, unfortunately, that aren't any better. In the UK, the average age is 5 years, so it's even longer than this. So clearly, if you could somehow figure out how can I diagnose this earlier, this would be good. Unfortunately, since we understand so little about the condition, there's no lab test that can either diagnose this or that can at least help you with the diagnosis. At least as of now, there isn't. And so let me give you one more background slide, and then I'm getting into what we've been doing with this. Traditionally, people had thought that autism is all genetic, and or at least 90% plus is genetic, and that's what you need to look at. People have revisited that over the last couple of decades and find out actually it's a combination. I mean, there certainly is a genetic component, but there's also a strong environmental component in there. Yeah. And so for our work, we decided saying, look, if it's roughly half and half what we're looking at, and there's a number of different hypotheses that people have of what may contribute to autism, why don't we pick one from each? Because on the genetic side, people are more and more focusing on epigenetics because just looking at the genes, they're not finding the risk factors that they were hoping for. And so it says, let's do something related to epigenetics and environmental factors. And oxidative stress is usually, it's oftentimes the result of environmental factors hitting. So we said, okay, well, let's focus on those. But we want to look at this at a metabolic pathway level, because I actually want to get an understanding, at least some of the things that are happening in the cells, inside of a patient that has an autism diagnosis. And so we focused on the folate-1 carbon metabolism and associate with the transsulfuration pathway. So here on the left, and I'm trying to draw a circle around it, this is essentially a folate-1 carbon metabolism. From folate that basically gets internalized, and ultimately here this conversion from SAM to SAW, that is driving DNA methylation, which is essentially your that's your driver for epigenetics. And you say, okay, so we have a pathway with a number of measurements of different metabolites that ultimately can look at DNA methylation. What we're interested in saying, would this work differently in children that have autism versus those that don't? Secondly, this pathway intersects down here with the transsulfuration pathway that leads to production of glutathione. Well, glutathione is the body's most powerful antioxidant. So if you have oxidative stress, most likely your glutathione levels are going to be abnormal as well. But one thing I want to stress is that people have looked at individual markers, like just glutathione or so. That's not helpful, because you cannot perform a diagnosis based on it. So you're going to have to basically take a lot more information into account. So what we did then, we said, okay, fine, let's have a look at clinical trials. In this case, this trial actually concluded before we did this work. But somebody at the University of Arkansas of America had the idea saying we recruited 83 children with ASD and 76 are typically developing. On top of that, not as important here, but we recruited 47 siblings of the children with ASD, but these siblings are actually typically developing. Okay, so genetically they're closer to these, but overall they should be much closer to typically developing children. And we're measuring here a panel of 24 metabolites and metabolite ratios. In addition to just saying that, well, somebody, do they have an autism diagnosis or not, we want to say a little something about severity. But there is no one autism severity score. You have different behaviors that you can measure. And one thing that people generally focus on is saying that we know that children with autism have a hard time when basically transitioning from one activity or one place to another. So this adaptation is something they struggle with. And so there is an adaptive behavior or composite score that gets computed, and that kind of tells you how well developed is the adaptive behavior. And so this tells you something about at least a subset of behaviors on the scale here. Now, the reason is that this was concluded before we did our work. People did the analysis. They found that, well, there are some statistical differences, but if I give you a blood sample, I cannot tell you what group you belong to. But what people have done, they had looked at each of these measurements individually, basically performed the t-test, calculated the p-value, and then decided are there differences. But for prediction, this was not nearly enough. So what we would then decided to do, and I basically want to give you a bit of a brief overview, is that when we look at this rather than one variable at a time, you want to look at multiple variables, because I may find one variable is a little high and another one is a little high, and each one individually doesn't tell me a lot. But if I combine them with, let's say, a third variable that's a little low, this may form a pattern that you say, oh, this pattern is somewhat unique to a certain diagnosis. So we're making use of multiple pieces of information. This is made up data, okay, to make the point. But let's assume you're measuring one metabolite X1 and another one X2, and I have a blue group and a red. And the one could be one having an autism diagnosis, the other one doesn't. If I just look at X1, I'm going to find that basically blue and red have more or less that the similar mean. There's not much of a difference here. And if I give you just the value of X1, there's absolutely no way you can tell me if that data point came from blue or red. Okay. If I just look at X2, I'm going to find red has a higher, has a higher mean, and also red has more of a spread. But for most part, there's a lot of overlap. Data could be either blue or red. You wouldn't tell. Fine. If it's down here, you would say it has to be blue. If it's up here, there's no red, there's no blue, so it has to be red. But there's a lot of overlap where you couldn't tell anything. By looking at both of them together, however, it's very clear that I can separate. I mean, I can draw a line through the middle. which is the same as if I'm projecting this on this line that's perpendicular to the line I've drawn, and then everything on the left is red and everything on the right is blue. So you can perfectly separate this. And this is Fisher discriminant analysis. What this does, and it's not restricted to 2 variables. I could take 5 or 10 or however many you want. Now, if you have more complex patterns, you can do similar things. There's a kernel extension to this. In this case, you're basically here, if I'm using a Gaussian kernel that I underlay this, then I can basically make a cut through here, figuring out everything above that's on this curve would belong to blue and everything below is red. Here in this case, I basically pick the radius. But these methods, they can automatically figure out where do you have certain patterns that it wants to basically separate. One other thing that's really important that often gets forgotten, is that we have our patient here, what I describe as real system. And then I have some model, and this model may tell you, for example, are you in positive territory, in which case you may have a diagnosis, or are you in negative territory, in which case you don't. But you want your model to basically reflect what's happening in the patient as best as possible. But you can't do this directly. You always do this indirectly because we are collecting data from the patient and hope that this data reflects reasonably well what's actually going on. But obviously there are measurement errors, there's ways how you design your clinical studies, there's maybe some bias in there, and then you have your model fit the data. But your goal is you want the model actually fit what's really going on. And so the problem often is if you fit your model too well to the data, it's almost certain that your model will actually not reflect the real system because there's some errors that you have in the data that are unavoidable, that suddenly these errors will make it into your model. And let me give you one simple example here to just illustrate this. So if I have a curve here and I pick a 4th order polynomial in blue, and in reality, you never know what that is, but I pick this and I'm plotting this curve here. Then I have these pink dots. Those are my data points from this blue curve, and they're reasonable data. I mean, they're not outliers. If I were to then saying, let's fit a curve through my pink dots, and in this case, I'm cheating even, okay? I know what structure I have. So if theta 1, 0 were exactly 1 and theta 1 is 1 and so on, I should get a perfect fit to my original curve. But I'm not fitting the curve. I'm fitting the data taken from the curve. You can see that, yes, here my black line, well, that perfectly goes through the data. But if I compare the black line and the blue, you're saying your model gives a poor fit, especially if you're somewhere out here, okay? So clearly in this case, you've overfitted. You are fitting your data perfectly, but you're not fitting the original system, your patient perfectly. If I picked something simpler here, like in red, and in this case, there is mismatch between my real system and my model. But if I basically do a best fit with this, I end up with the red curve, which is a much better approximation. And so this is something we definitely have to avoid, okay? Because the reality is, especially in this day and age where people want to do a lot with deep neural networks, they have so many parameters, I can fit anything. The value is not in fitting your data. The value is in predicting parts of your data you've not used. That's what we're trying to do here. And so the way we go about this is that you take your samples, and you have your model, and the model, based on the samples, can predict errors. But what we're trying to evaluate is something called leave 1, or there's also leave x, where x can be other numbers other than 1, cross-validation. So I'm taking a sample out, I'm building my model with the rest, and then I'm predicting only the one sample that I've left out. I put the sample back in, take the next sample out. I'm building a new model, and I'm only predicting that one. And so in the end, after I've left every sample out, I have errors. And in each case, the error is based on something that my model didn't know. Now you have to then go in and saying, now I make my model more or less complicated, and I repeat this. And you're going to find that actually, as if your model gets too complicated, you're starting to overfit, and actually your errors start to go up. Whereas for fitting, the more complex your model, the errors will always go down. It's just, that's not useful information. So, and if you apply this now to the data we have for our ASD trial here, then you can actually find that by using 7 variables, we can almost perfectly separate the group of typically developing children based upon their metabolites from the group in blue, which is the group of children with the autism diagnosis. You can see here's the probability density function. There's some overlap. It's not a perfect separation, but you can do this quite well, and basically you get like 95% plus accuracy. As a side note, for a 2-year-old, the gold standard is that a psychiatrist uses something called the ADOS tool. That's about 80% accurate for a 2-year-old. That's more accurate as people get older. So, but if you basically can get over 80%, that's certainly an acceptable value. Here are the variables that I used, because actually out of the panel of 24 measurements we had, we didn't need all of those. We just needed 7. Yeah, but interesting, DNA methylation and the percentage of oxidized glutathione, those come out as the top 2 variables. And that's interesting because we started by saying, well, let's focus on oxidative stress. And that's basically related to your glutathione, and on DNA methylation, well, that's what we're measuring here. So clearly, this was a good choice. To put this in numbers, out of the 83 people with the diagnosis, we got 81 correct, and the 76 who are typically developing, we got 73 correct. Some people are always worried, it's like that we don't want false positives because we rather miss a few people. Well, that's fine. All you have to do is, I picked this cutoff somewhere that kind of cuts this area that overlaps in half. You put the cutoff down here, then you don't have any false positives. And you're going to find that, yes, I'm going to miss a few more people for the autism diagnosis, but it remains above 90%. Okay, so very easy fix. All you have to do is drop the line a little lower. Okay, and that's really a choice we get to make. And I kind of summarized what's on this slide, and I said, key here is that our assumption to look at oxidative stress and DNA methylation, we said that it seems like we're on a good path here. That kind of got verified in the process as well. Yeah. Now, is that we've shown that we can do classification, but how about, can we predict this Vineland score? Yeah? Can I use the same blood samples in order to figure out how is the adaptive behavior changing with this? And for this, we basically use the regression model. I mean, you have your ordinary least squares regression, which basically takes your data X and tries to predict Y. That's not so good here because you would be overfitting terribly. Yeah, you can use principal component regression. Well, that tries to find get all the correlations in X out, or you can use partial least squares, which removes more correlations with an X, but also Y, as well as between X and Y. So that's better. Last but not least, you can do, rather than finding a linear transformation, you can do a nonlinear one and end up with kernel partial least squares. And that's exactly what we ended up using here. So if I use kernel partial least squares, then with a model of 5 variables, I can actually predict this reasonably well with R squared of 0.45. Yeah, it's not something that, yes, whether it would replace the observation, but it is a good indicator. For these types of studies, that's a very high value, actually. We would have been happy with anything 0.3 and above. That's kind of what we're shooting for. So in a summary, as of now, you don't have any reliable biomarkers for ASD. There's no test on the market. But using this from this one study, we've shown that actually if you measure metabolites and then use Fisher discriminant analysis, which is a machine learning method, you can actually nicely separate the children who have ASD from those that don't, and you can actually predict this. Yeah. On top of that, the adaptive behavior you can predict reasonably well. So there's significant potential because literally there was actually nothing like this that was done before. Like with any study, you need to validate this. Yeah, and I'll get to that in a second. But first, when we published this, yeah, we got a lot of press. Okay, I mean, it made the journal cover. We got a very high altmetric score, and within 2 weeks, this was really picked up by all major news networks. Yeah, this was from Reuters, ABC, CBS, NBC. You mentioned it. For 2 weeks, my phone kept ringing, which is something I've never had before in my career. Okay, it's not like this usually happens, but it was unusual. So I was surprised. Yeah, but that's only one part of it. So clearly there's a lot of interest, but ultimately you want to see like, well, can we use this somehow to develop a test and get this into the hands of doctors? Yeah, and a couple months later, I got an email from somebody who says, well, I work in the venture capital space. I quit my job. I started a company. I want to license your IP and I want to develop this test. And this company is called BioRosa. And literally the only goal is to take the knowledge that we have here and turn this into a test that they can market to physicians. Yeah, this is they're working on this. Okay, they raised several $1 million, so they have the money to run another clinical study, but that's going to take a while. Yeah, and if you look at their website, a lot of the things I used in my presentation show up again. That yes, if you have earlier diagnosis plus intervention, you have better outcomes, and there's what the cost is, and so on. So that's currently going on. By the way, I'm not the founder, nor do I'm an owner in BioRosa, but they used some of my work, and it's kind of neat to see that, well, depending on how this goes, maybe we'll actually have a test on the market that's based upon some of the research that we've done. Yeah. But one thing that we did in the meantime, is that running a new trial is expensive, but why don't we basically look at ongoing trials so we can use this? Now, given that these trials were in the planning stage, we said, fine, we had to look at trials that we are used for treating ASD, because running a test where you have a control group of just typically developing kids, it's very hard to convince them to participate in this if there's zero benefit for them or anybody like them in there. But there's a number of studies where people used these similar measurements and they took them at baseline. So there was no treatment was done. So, okay, at baseline, that's like exactly what we want. And so we have a study of 154 children. All of these had an autism diagnosis. Unfortunately, they didn't take our metabolite panel of all 24, they only used 22, and the two they're missing are the DNA methylation and HOHG, both of which turned up to be in my top 7. So I said, well, in order to adapt this, if I go back to my old data and I pretend I didn't have those two, so I just deleted them and saying, what is the new best model we get? And then I just took this model and applied it here. Okay, so this is just purely testing. And you find that on the original data, but now with 5 instead of 7 metabolites, you got a reasonably good separation between the typically developing group in red and the one with ASD in blue. And now if I use my validation set, which is really just pure validation, there's nothing that they've done to the model, you find out that we still get 88% correctly predicted. And given that, I said, anything above 80 is acceptable. And so we're certainly in good territory, and this looks very promising. So that's in a nutshell, that we identified some key mechanisms here. And we basically have now 2 studies that already show that, yes, you can distinguish between the children with an autism diagnosis and the ones without based upon this metabolite panel. But the real key is you have to look at numerous metabolites all at the same time. If you look at them one by one, you will not find anything. You may find that they're statistically significant. You cannot predict. It just doesn't work. The data science aspect is absolutely key for this work. So what we then decided, like, this gets me to the next topic. But we're going to stay with the same pathway. But if somebody wants to plan an intervention, long-term out, maybe somebody says, well, let's develop a compound that can basically affect this folate 1-carbon metabolism. Usually, you're not targeting the metabolites. You are targeting the reactions between the metabolites, and usually by changing some enzyme activity. That's what you're usually doing. So we said, fine, so we need to actually build a model to figure out if basically I have these reaction mechanisms. And by the way, this is a different or a simpler representation of the same pathways we've looked at. But I want to see what are the reaction parameters that we're interested in. Now, there's no dynamics in here. We have one data point. So it has to be, you have to look at this at steady state because I can't do dynamics from one data point. But I can write my model by basically writing valence equations for each of the components. And I have the measurements from the components that I can then basically use in order to get my parameters. Really important here, we are interested in getting the distribution of the parameters and not just the mean values. Because this is, as I said, it's a very heterogeneous group, and you're not going to find that there's one mean value that represents everybody well. We had to make a few assumptions to simplify this, but ultimately, we formulated this as a nonlinear programming problem where we estimate these parameters. Some of the values for the outputs you can actually find in the literature that other people have measured. And when you do this, then we had to make some other assumptions related to, like, you see this reaction here, there's a 4 in reverse. Well, you're not going to be able to get both of those. So you can get, for example, the ratio. And so you had to further simplify that because with the measurements you have, it just would be underdetermined. But if you formulate this the right way, and then you plot your probability density function of these parameters, you see that there are some of them that are actually significantly different, like over here, this one is very different. Others here are very, very similar. And you can say, well, if you want to target an intervention, you could try to figure out, for example, could you make this PDF here with an intervention, could you get it closer to what the blue curve looks like? But what we did in the first step is that we wanted to identify where interventions would be most likely to have an effect? And then secondly, can we tie this to something that we already understand? And if you do this, then you actually find again that this is related to several of these activities, and they're either related to oxidative stress, to methylation capacity, which deals with your DNA methylation, or it is directly linked to oxidative stress. So these ideas, again, to look at oxidative stress and DNA methylation came out of this study as well. And now you basically, but now you have a few points we can say, well, I can intervene if I can figure out how to change the activity of these three enzymes that I'm interested in. Okay. Now, that's kind of in a nutshell what we've done here in the second part. The third and last part I want to get to is that we want to have a diagnosis by 18 to 24 months. But maybe you can figure out, maybe this would actually work earlier, when you cannot really observe any kids, but maybe there are signs already present. In the most extreme case, and that's what we're trying to do here, maybe you could figure out if I actually take measurements from the mothers during pregnancy and see what happens. And so we decided, fine, let's have a look at the study. This is a really complicated study, okay, because you're looking at mothers during pregnancy. Well, they have to give birth, and you have to wait a few years to figure out will the children have an ASD diagnosis or not. We limit us to 3 years in this case because you still have to follow for almost 4-year period from beginning of pregnancy until this time. And on top of that, the big problem you run into is that, autism prevalence is 1.9%, which is high. But if I run a study with 200 participants and I don't know the outcome yet, outcome being will they have an ASD diagnosis or not for a child, that means I would have roughly 4 children with a diagnosis. There's no way I can do any statistical analysis. But running this study with 2,000 or 5,000 participants is really unrealistic. To be honest, this study that I'm going to draw on here, this went on from 2006 to 2017. Okay, this is a really long study. It was very difficult to conduct. But if you look at if somebody had 1 child with autism, the probability that the next one has autism is actually tenfold. It's 18.7%. You say, fine, if I just look at what you would call a high-risk population, I can run a study with a little over 100 people, and I will have a reasonable sample size to draw from. Okay. And so this year, as I said, we had data from a total of 129 mothers, and this was done at the Mind Institute of UC Davis. And they basically had these mothers all had 1 child with autism already, and then we had 107 of them did. And then we had another 22 which did not have any children with autism. And so he basically took the blood samples during the first, second, third trimester, and then we wanted to make a prediction based upon later on, could we predict the child will or will not get an autism diagnosis? Now, here's the breakdown. You see, we actually had a good number. We had almost everybody for the second and third trimester. For the first one was hard because, well, the women didn't necessarily know that they were pregnant yet for the initial part. And then they probably had better things on their mind than saying, oh, let's see if there's a clinical trial I can participate in. But it's still a reasonable number. But when we analyzed this and we first did the univariate analysis, there's almost no difference. We found like 2 measurements that are with the t-test just slightly significant. And when we then said, fine, let's use our multivariable techniques, you end up with absolutely horrible prediction accuracies. Okay, when we basically, if you have a type 1 or type 2 error of 50%, I can flip a coin. That's as good as this. So we ended up with 30 to 40%. So that was clearly not the answer. Saying, no, you cannot predict if during pregnancy based upon this, the child will have autism later on. Now you could ask, well, why are you showing these results if you can't predict this? There's something else we can do. And I said, so far, we've used the data from all the mothers that already had 1 previous child with autism. So we know they're in a high risk group. Then we have a certain number of mothers we just sample from the regular population. We know that their risk is around 1/10. So we said, fine, maybe we can find a difference between the two. You can argue, why is that important? Well, if you already had 1 child and a child had autism, it's not. But before you have your first child, you don't know if you're in a high risk group or not. So, and on top of that, we do know there are some interventions, like for example, making sure that folate intake is at a high level, that actually during pregnancy that actually reduces the risk of the child having autism later on. Yeah, and so basically, if you find out somebody would be at a high risk, you can say, well, here are some steps you can take that minimize your risk. So knowing that would be important. So we do the same thing, except now we're comparing the mothers that we know had a child with autism versus those that were just sampled from the random population. And you find that then even when you look at the univariate analysis, everything in gray here says it's statistically significant. There's quite a bit in each of the 3 trimesters. When we then basically build our multivariable models here, and I said, I can take one model and look at where does it work best? Well, it turns out during the 3rd trimester it works best. Or I can develop a separate model for each trimester and just work there. You find that, yeah, it's not going to be 100%, but you get, basically, you get about 90% right, maybe 85% at the worst. But it's, in general, you're looking at 90% plus, which is a good thing. Yeah, so basically, the outcome is I cannot predict if a child may have an autism diagnosis. From a purely ethical point of view, I'm actually happy it turned out that way. Okay, but at the same time, you can predict if you are at the higher or what to say or normal risk of having a child with autism. Yeah, but keep in mind 18.17%, it's a high risk, but it also means that you have an 82.3% that will not have that. Yeah, so that's still the much more likely outcome. And so this is something that seems to be correlated with this. Obviously here, given how hard that trial was to conduct, I don't have a follow-up from that. Yeah, but let me summarize, come to the end here. So when you look at metabolites of the folate 1-carbon metabolism and the transsulfuration pathway, you find that there's a strong correlation with autism. Yeah, they can be used to support the autism diagnosis. Yeah, and they give you reasonable prediction for adaptive behaviors. And if you look at basically the same metabolites from mothers during pregnancy, you find that there's a difference based upon if they have a high or regular risk for having a child with autism. One thing I want to stress here is that if you run any of the things I've done, but you use univariate analysis, analyzing one measurement at a time, even if you have 50 measurements, you are not going to be able to draw the conclusions here. So the data science abstract is absolutely key to being able to do this. Yeah, and that's ultimately, my group is a data science group. So for us, this was a very nice outcome. That's basic, nicely complemented what's being done there. Well, I want to acknowledge a number of people. That's the students in my group, in particular, Troy Vargason, Katie Hollywood-Jones, and also Daniel Hausmoon, who basically did most of the work that I presented here. Then a number of collaborators, because I do not run these clinical trials. Yeah, I mean, I serve on the DSMB for some of them, but I don't run them myself. And then, of course, a number of funding agencies as well as foundations that help us provide funds. And the one thing that I usually want to end is that usually when people hear about autism, they always think talk about the brain. And I think that no, this affects your whole body. You have to think beyond the brain for this. And I want to thank you for your attention.
So thanks so much, Professor Hahn, for this outstanding talk. And so before I go to the Q&As, I want to call everybody's attention to our upcoming hybrid seminars. As you can see, we have amazing sets of speakers ready to present this semester. And next Friday, October 1st, we'll hear from Professor Ron Fan from Yale University as he presents Space Adventure, the next wave of biology revolution fueled by spatial omics technology. So please follow us on social media to receive latest update. You can see our social media information on the slide, and you can always access registration information for our BME seminar on the website, and then we are actively to developing more programs such that will be widely available, not just to our own students in here, as well as outside. So now we're open for questions, and then there's a question in the back.
Hi, thank you so much for your talk. This was really interesting. I was wondering why you chose to start predictions of maternal blood samples, and whether you would expect that you repeated the predictive study with like newborn or 1-year-old blood samples, whether you might better be able to like perform predictive studies using the patient's blood itself.
Dr. Hahn, can you repeat the question?
Yes, that's it.
Very long.
I will repeat the question, but I also ask that you tell me if I understood it correctly. So your question is, why did I analyze the blood samples of mothers rather than, for example, looking at newborn, 6 months old, 12 months old? Why did I go back all the way to pregnancy rather than basically looking at younger children? Is that the question?
Yes.
So, two reasons, okay? I mean, number one is each of the two ways would be about equally complicated, yeah? Because in both cases, you are taking samples from children or mothers where you don't know the outcome yet. So you're going to have to track them, yeah? And so one is as difficult as the other. The reason we picked the mothers was because at UC Davis, they had been recruiting mothers and been freezing their blood samples in 2006. Now, they hadn't done the analysis yet when we came along, yeah? But they said, okay, well, you have a data set, yeah, that, yes, I need to get my collaborator to do the metabolomics on it, which they did, yeah, but at least all the samples are already taken. For children, it is something we're looking at to a large degree, like many things in science. You have to find somebody who funds this, right? I mean, you can, for children, for example, we have some plans to look at, can you look at the cord blood samples, because those are often also frozen, yeah, and they get stored for many years. And so I could go back figuring out who has an autism diagnosis, contact then, or you have to anonymously do this, obviously, saying, well, the families, would you be willing, yeah, to basically donate some of the cord blood for the study? Yeah, not the easiest thing, because usually the reason they store the cord blood is because if there's some health conditions that can help this. And but I mean, you don't need the entire amount, but it's certainly a decision that people will have to make, and it's not the easiest one either. But for the mothers, the reality is the samples were more or less readily available for us. That was the reason. Looking at younger children is definitely on the to-do list. Yeah, and it's something we're interested in. But well, maybe I'll come back in 10 years and I'll tell you how it went, right? So, but it will take us a while. So it's on the drawing, in the drawing block.
Yeah, in blue shirt.
Yeah. What's the end game of ADS research? Is it like to get the earliest diagnosis possible? Is it to find a cure? Or?
I mean, so the question is, what's the ultimate goal? Is it that you want an early diagnosis? Do you want a cure? I mean, I think there are several things you're looking at. Number one, you want as early a diagnosis as, well, maybe not as possible, but as early as you can do something about it with interventions, okay? Like the current interventions, the behavioral therapies, if I knew at birth something is there, I mean, your kid's not going to go through behavioral therapies at 2 months old. Yeah, you probably wouldn't start those. I mean, you would have to get to a further stage in development. Yeah, but you could start earlier than 18 months if you can diagnose. So the question is 12 months the right time? There's no exact answer, yeah? But the 6 to 12 months range is probably what we would be shooting for. Yeah, so if I knew it from cord blood, for example, at birth what happened, that would be good, but you probably don't do anything. Now, I don't think there is a cure. I don't think it's ever going to be a cure. Okay, but there's things that you can be doing in order to basically improve people's lives throughout their life. Yeah, and so if you can essentially make sure that if you can, with earlier intervention, yeah, hit this early on, so that a very severe case would turn into mild to moderate case, I would call this a big success. Yeah, this idea of a cure, I'm very skeptical there. I mean, there are some people who are very, very mild autism to start off with, and some of them lose the diagnosis. We're talking about 10% roughly, yeah? But the people who are very strongly affected by it, I mean, never say never, okay? We're early on the research, but I think we're talking about improvements over the lifespan. That's what we're shooting for.
So I have two possibly related questions. The first is, what was the distribution for the ages of the patients you've got samples for your original classifier. And then when you showed the original classifier, it perhaps showed on the patients that have ASD like a bimodal distribution. Do you think that that is actually bimodal or an artifact of the data you're collected, and or could it represent distinct subtypes of metabolic populations for which the classifier could perform better?
Excellent questions. Let me briefly, well, you asked a long one. Now you have to jog my memory. And so you're basically, yeah, your second question was that there was a slight bimodal trend that the classifier showed, and if this is indicative of subtypes. The second or the first question was that no, I forgot the first. Oh yeah, the first question, the age range. Yeah. So let me answer age range first. Okay. So for the original data set, the age range went from 3 to 10 years old. Yeah. For the second study, no, sorry, 4 to 10 years. For the second study, it went from 3 to 15 years old. So it was actually, even though we were predicting, it was slightly larger range. So I didn't have anybody with 18 or 24 months because honestly, it's very, very hard to get that, especially they either don't have a diagnosis or they just got one. And the first idea on parents' mind is not to basically engage in a clinical study, yeah, especially a clinical study that just helps with diagnosis, which they already got, yeah. So that was the bimodal. That's a good question. If I looked at this data by itself, I think it's more an artifact of the study. I don't think. Now, are there subgroups of autism? Absolutely, yeah. We just have to figure out how to best characterize them, and we can't exactly agree on how to do that yet. I had an entire PhD thesis on subtyping of autism, yeah, but what we decided to do is we went by co-occurring conditions, yeah, and so we basically looked at who has epilepsy, who has GI problems, who has sleep problems, and that was actually a huge study because we worked with medical claims data, and so I had 100 million patients that I could search through. But then when I restricted it to saying you have 5 years of data, yeah, so they couldn't change their medical providers in 5 years, we were down to still 250,000 people. Yeah, but I had data from 250,000 children from birth to age 5, and we did some subtyping there. And we found that I think there's at least 3 distinct subtypes if that's the criterion you use. Yeah, other criteria may also be possible, of course, and there's no general agreement. But there's no doubt in my mind that there are subtypes. And in fact, this is speculation, okay? So don't quote me on this. Yeah, but just because we have an autism diagnostic code that's based upon behaviors, yeah, I'm not so sure that this is all the same condition. Yeah, I think these subtypes are so distinct that maybe in 10 or 20 years, we may look back at this and saying, oh, there's 3 or 4 different conditions, and then maybe call it whatever. And they were all lumped together into autism at one day. It wouldn't surprise me. Yeah, we're not there. That's not. But there's a number of people, not just myself. They talk about autisms in the plural, already indicating, well, this is maybe more than just one. And this may also be indicative why. I mean, there's some people who are very, very mild on the autism scale, but who basically, as they have jobs, they have families, they live perfectly happy lives. And there's others who need 24/7 care and can't even do the simplest things themselves. Yeah, I'm not so sure that this is necessarily all the same, even though right now they all have a diagnosis of autism. I think this will sort itself out, but it will probably take a while. Yeah.
Have kind of a broad question. And also because like when you're sitting there, you have a
So question is basically, do we know what causes ASD? And if you, for example, find that if you have siblings with ASD, that the likelihood of a next sibling also having ASD is higher. Look, this is the million-dollar question, okay? Nobody exactly knows this. Now, do we know certain risk factors that increase the risk? Absolutely. Yeah. For example, one thing that often comes to mind is if there's Now, if there's infections during pregnancy that result in fever, that oftentimes increases the risk. Okay, that's one of the things we found. Children that are born preterm are more likely to have ASD. Yeah. What other factors? I mean, there's certain medicines that are not being prescribed anymore that dramatically increase the risk of having a child having ASD. Okay, took a while for people to understand that maybe these shouldn't be prescribed during pregnancy anymore. But that's not the reason for the increase we're seeing. Yeah, but certainly that's another factor. Depression in the mothers is a risk factor. Yeah, we're still trying to figure out that it doesn't look like as if. So if somebody treats the depression, it's not the medicine that's causing it. It more seems to be that if generally the diagnosis was already the increase. But we're talking about a number of risk factors. The increase is 20%, 30%. Now, 20% may look like a lot, but if you're saying, well, the probability to have autism diagnosis is 1.9%, the 20% increase puts you at 2.1%. Yeah, that's not so dramatic. There is no smoking gun out there. I think it's going to be a combination of factors that ultimately increases this. By the way, this is the thing where traditionally people thought this is all genetic and they focused a lot on genes. But we've done numerous studies and spent over $1 billion on genetic studies. And right now, the best result they can give you is that in 90%, they don't even find genetic risk factors. In the other 10% where they find genetic risk factors, these risk factors increase your risk this much. Yeah, so clearly it's somewhere there, but it doesn't necessarily tell you a whole lot. But the reason why there was this change when people thought it was all genetic to saying, oh, environmental factors. These studies were not necessarily conducted, or there were, well, I don't want to say proper care because it's not appropriate, but people looked at these studies a little differently. Initially, you said you focus on, for example, twins and saying, well, they're identical twins, the genes are the same. They also shared the womb environment during the same time, okay? So if there were environmental risk factors during pregnancy, both of them were exposed. And these are the things that we're now trying to tweeze out, whereas before this got lumped together. Yeah, and so, but there's no perfect answer out there, and I'm just somewhat skeptical. If I look at the popular literature, they tell you things like maternal age is really important. It's a risk factor. It's not big. Basically the studies we did with 100,000 mothers, the average age that we had for children with the ASD diagnosis was less than a year more than the ones without. I don't think that's what the driver there. Yeah, we're still looking. I wish I had a perfect answer for you, so that it would with many other people, but it's a very complex problem.
So
But-
I'm going to take one from the virtual. Oh, I'll take one question from the virtual audience. Hold on. And then I think that's going to be our last one because we're already towards over noon. So I thought there are a lot of good questions here, but I thought I'd go for the one with the sort of entertainment value, which is Elon Musk stated he has ASD. What portion of cohort function at a high level, and do geniuses tend to have ASD?
All right. I think I set myself up for that one. I said, so two things there. Yeah. I said, it's a very heterogeneous group. Yeah. Elon Musk may have ASD diagnosis. I'm not so sure Elon Musk needs any help. Okay. He's very successful. Yeah, he basically, he clearly can do his job well. Yeah, he also has other relationships. So he may have ASD diagnosis. People like Elon Musk are not really on my radar when I'm doing my work. That's not, look, this is, somebody has a diagnosis or not, I don't think it matters. One thing I do want to clear up, because this is often brought up saying, oh, but people with ASD, they're going to have some other gifted skills. They are no more or less likely to have special skills in some areas than the general population. It's one of those myths that are out there. Statistically, it's the same. Yeah, so you have some people with special gifts with ASD, and you have some people with special gifts without ASD. It's no more or less likely. But this talk wasn't about Elon Musk or people like him.
Anyway, well, let's thank our speaker.